Will somebody be checking the Slack channel?
Hi, Divya here. It's 9:29. Do we want the YouTube link to go live now? Yeah.
It's already live, Dev.
Perfect. Okay. So it's already streaming, right? Yeah.
Yeah, so I have to give signal to Crispin to unmute from there.
But we should still be recording here, right?
I'll start that.
Please record to cloud, Harvinder. Yeah.
Geeta, I think you can start.
Shall I?
I think so, yeah.
Please go ahead.
Yeah. So a very good morning to everybody. I welcome you all to this special session of public lecture, which has been organized as part of the 39th annual meeting of the Astronomical Society of India. I'm sure while some of you have joined as participants of the ASI, many more of you are joining us on our YouTube channel as general audience. A very warm welcome to all of you. As we know, the 2020 Nobel Prize for Physics was shared by Sir Roger Penrose, Professor Andrea Ghez, and Professor Reinhard Genzel for their groundbreaking research on black holes. As members of the organizing committee of the 39th ASI, we thought that a public lecture on this dense but fascinating topic will be of great interest to young students and also to the general audience. The big problem was to find someone who could deliver this lecture, as not many people understand this topic well, and still fewer are capable of engaging a wider range of audience that is expected at the ASI, like academicians, young researchers, students, postdocs, and general public, all at one forum. So one accomplished and internationally renowned expert who we knew could do this is Professor G. Srinivasan, formerly at the Raman Research Institute, Bengaluru. He readily agreed to deliver the public lecture on this obtuse subject and also to expound on the key research findings and discoveries for which the Nobel Prize for Physics was awarded. On behalf of the organizing committee and on my own behalf, I thank him for delivering this lecture and extend a very warm welcome to him. We are especially grateful because he agreed to take time out and for this lecture on a Sunday morning. Before we invite him to speak, I would also like to welcome Professor Dipankar Bhattacharya of Inter-University Center for Astronomy and Astrophysics at Pune, who will be chairing this session and will also introduce Professor G. Srinivasan. Professor Bhattacharya himself is an internationally well-known astrophysicist and also a former student of Professor Srinivasan. I invite Professor Bhattacharya to take over, please.
Thank you so much, Nandita, and thank the ASI SOC for giving me the opportunity to chair this session. I would like to welcome you all to this public lecture organized as a part of the 39th annual meeting of the Astronomical Society of India. Thank you very much for tuning in on Sunday morning. I'm sure you're in for an incredible treat. So there will be this lecture, and after the lecture, there will be question and answer session. So those of you who are on Zoom, you could raise your hand from either the raise hand button at the bottom of your screen or under the reactions tab. And we will then take those questions and we'll request Professor Srinivasan to answer them. And in the YouTube channel, you could raise your questions in the chat box, which also will be read out and for him to answer. So it is now my pleasure and honor to introduce Professor G. Srinivasan, the speaker of today. Professor Srinivasan is one of the most distinguished astrophysicists of India. In his early career, though, he was trained as a condensed matter physicist, obtaining his doctorate degree at the University of Chicago, and thereafter spending several years in Europe and the United Kingdom, during which he worked in premier institutions like the IBM lab in Zurich, the Chalmers Institute of Technology in Gothenburg, and the Cavendish Laboratory in Cambridge. In the year 1976, he decided to return to India and join the Raman Research Institute in Bangalore. This marked the beginning of his career in astrophysics. Since then, he has made numerous pioneering contributions, particularly in the area of neutron stars and pulsars. Along with Professor V. Radhakrishnan, he introduced the concept of recycled pulsars. And following that, he correctly predicted the nature of millisecond pulsars. He predicted that millisecond pulsars would be bright gamma ray emitters, long before this was confirmed by NASA's Fermi satellite. He also provided important new insights on how the magnetic fields of neutron stars can change with time. These are just a few examples of many far-reaching scientific contributions that he has made. To a vast population of students and indeed general public, Professor Srinivasan is known for his scintillating lectures, many of which are on YouTube and are extremely popular. He has taught and mentored generations of students, myself included, with extraordinary amounts of passion and skill, enabling them to achieve their potential, for which we are eternally grateful. Professor Srinivasan has also served the astronomy community as a whole in various important roles. He played a key role in conceptualizing India's first space astronomy observatory, ASTROSAT, and guiding it towards realization through his detailed and meticulous reviews in the ASTROSAT Payload Monitoring Committee. He led the commission and later the division on space and high energy astrophysics of the International Astronomical Union for a number of years. He was the secretary and then the treasurer of the Indian Academy of Sciences, under the auspices of which he authored a much respected decadal vision document for the astronomy at the turn of the millennium. During this period, he was also the president of the Astronomical Society of India. And we heard yesterday from the current president of the Astronomical Society of India that the society is now embarking on such a vision document for the years to come. It is indeed a privilege to have Professor Srinivasan as a public speaker today. We excitedly look forward to his lecture, in which he will take us on a tour of stars and singularities, bringing to focus the discoveries that led to the 2020 Nobel Prize in Physics. I am delighted to now call upon Professor Srinivasan to deliver his lecture.
Good morning. At the outset, may I thank the organizers of this meeting of the Astronomical Society of India for inviting me to deliver this public lecture, which they intend as a commemoration of the recent Nobel Prize for Physics. I also wish to thank my dear friend Dipankar Bhattacharya for his kind and very generous introduction. Last year's Nobel Prize for Physics was awarded jointly to Sir Roger Penrose, Reinhard Genzel, and Andreas Ghez for their remarkable work concerning black holes. Now, black holes have very much been in the news in the last few years. A couple of years ago, the Nobel Prize for Physics was awarded for detecting gravitational radiation from two coalescing black holes. And of course, the picture of the shadow of a black hole as synthesized by the Whole Earth Telescope was splashed in every newspaper around the world. Therefore, the public is very much aware of the recent and exciting discoveries concerning black holes. Therefore, in this lecture, I will stay away from the recent discoveries. Rather, I will go back in history and recall for you some of the momentous discoveries, because I think by doing so, you will be able to better appreciate the profound significance of the discovery made by Roger Penrose 57 years ago, which not only triggered a great revolution in black hole research, but which is at the base of the present revolution in cosmology. The citation for Genzel and Ghez reads as follows. They were awarded the Nobel Prize for the discovery of a supermassive compact object at the center of our galaxy. Genzel, Ghez, and their large number of collaborators observed the motion of stars that orbit the dynamical center of our galaxy by observing in the infrared region and by using very clever adaptive optic techniques. These were exceedingly difficult observations requiring very innovative instrumentation. To arrive at their final conclusion, for which they were awarded the Nobel Prize, they had to observe and gather data for more than a decade. By observing in the infrared and using adaptive optics, they were not only able to detect the stars that orbit the center of our galaxy, but they were able to determine their velocities and even acceleration. What did they find? One, that the object at the center of our galaxy is an extremely compact object. Two, it is very massive with a mass in excess of 4 million solar masses. But why the excitement? Well, if you have such a large mass and it is very compact, then it is either a black hole or will soon become a black hole. Now, black holes come in different masses. The overwhelming majority of them will be of stellar mass. Estimates suggest that in our own galaxy, there must be more than 100 million stellar mass black holes. In addition, most galaxies, if not all, have supermassive black holes at their centers. Their masses vary from several million solar masses to several billion solar masses. And let me remind you that there are more than a million galaxies in our universe. Therefore, there are an awful lot of black holes in our universe. Our story begins in the year 1783, 100 years after Newton published his Principia. John Mitchell was a pastor in a small church in Cambridge. He was a natural philosopher and an extraordinary scientist. He wrote, in my humble opinion, one of the most remarkable papers in the entire history of science. Using Newton's ideas on gravity and Newton's idea that light consisted of corpuscles, he argued that if a star of mass m were to have a radius equal to 2 gm by c squared, where c is the speed of light, then such a star would be invisible. Why? Let me remind you that according to Newton's laws, the escape velocity from an object with mass m and radius r is equal to the square root of 2 gm over r. Therefore, when the radius of the star becomes equal to 2 gm by c squared, the escape velocity from the star becomes equal to the speed of light. Therefore, any star slightly smaller than this would be invisible to a distant observer. Now, this is an incredibly remarkable statement for two reasons. One, of course, is this conjecture. The second is that I want you to appreciate that in 1783, no one was worried about the nature of the stars. Indeed, the positivist philosophers who were very influential in European thinking had asserted that it is in the very nature of things that we shall never know what the stars are. And yet, John Michell went on to conjecture why certain stars would be non-luminous. Now, this idea went from John Michell to Benjamin Franklin in America, and through the American ambassador to France, it reached the great mathematician Laplace. And in his very famous book published in 1798, Laplace wrote, "A luminous star of the same density as the Earth, and whose diameter should be 250 times larger than that of the sun, would not, in consequence of its attraction, allow any of its rays to arrive at us. It is therefore possible that the largest luminous bodies in the universe may, through this cause, be invisible." 10 years later, when the second edition of his book was published, he removed this paragraph. What had happened in the intervening 10 years? Well, Huygens in Holland and Young in England had discovered the phenomena of the interference of light and concluded that light cannot consist of corpuscles, light must be a wave. And no one, not even the great Laplace, knew how to deal with a wave in a gravitational field. For that, we had to wait till November 1915, when Einstein published his new theory of gravity, the general theory of relativity. Now, according to Einstein, gravity is not a force. Remember that Newton said the apple falls to the ground and the moon is falling towards the earth because of the force of gravity. Einstein asserted that there is no such thing as a gravitational force. The acceleration that bodies experience is due to the curvature of space-time. The presence of mass curves space-time. Let us look at a flat space-time, a two-dimensional representation of it, as shown in the picture on the top. Objects in such a space-time will either be in a state of rest or in uniform motion in a straight line, as asserted by Newton in his first law of motion. However, if there is matter present, it warps space. And this curvature of space causes test particles to accelerate or decelerate. Therefore, according to Einstein, gravity is not a force. It is merely the curvature of space. Now, the general theory of relativity makes several new predictions. One of them was that light will be affected by gravity. We already knew from the special theory of relativity that since light has energy, it has an effective mass. And what the general theory of relativity tells you is that light will be deflected by gravity just as a stone is deflected by gravity. The second effect predicted by the general theory of relativity, not quite the general theory of relativity itself, but the principle of equivalence, which is at the base of the general theory of relativity, the second effect is the gravitational redshift. Imagine shining a torchlight perpendicular to the surface of the Earth. As the light wave climbs against gravity, its potential energy will increase. In the case of the stone, the increase in the potential energy of the stone comes at the expense of the kinetic energy of the stone, and the stone slows down. However, light cannot slow down. Remember, the energy of light is equal to h nu. Therefore, what happens is that the frequency of radiation will decrease. Therefore, as the wave climbs against the gravitational potential, the wave will be stretched to longer and longer wavelengths, and this is known as gravitational redshift, and this will play a central role in our discussion of black holes. The general theory of relativity predicts two qualitatively new features. One is it predicts the existence of gravitational waves. They were detected a few years ago. And the second, it predicts the occurrence of black holes. And that's what we shall discuss now. Einstein published his new theory of gravity in 4 short publications in November 1915. Within a month of the announcement of Einstein's discovery, Karl Schwarzschild had found an exact solution to Einstein's equation. He sent a letter to Einstein describing this exact solution of the nature of the geometry of space-time exterior to a spherically symmetric star. Einstein was astonished by this. He almost fell out of his chair because Einstein believed that his equations were so complicated that it was extremely unlikely that anybody would ever find an exact solution. And Karl Schwarzschild had done so. And Einstein went before the Prussian Academy and read Karl Schwarzschild's paper. Within a month, Einstein went before the Prussian Academy for a second time to read a second paper by Karl Schwarzschild, in which he had described the nature of space-time inside such a spherically symmetric star. Now, what is extraordinary is not only the intellectual achievement of finding an exact solution, but the circumstances under which Karl Schwarzschild found this solution. Remember that in November 1915, the First World War was raging. Germany was at war with Russia. Karl Schwarzschild was a senior officer in the German army, and he was fighting on the Russian front. And it is there that he made these 2 remarkable discoveries. Within a month after that, Einstein appeared for a 3rd time before the Prussian Academy, this time, sadly, to announce that Karl Schwarzschild had died in the battlefront. He contracted a terrible disease and died. Karl Schwarzschild was an extraordinary mathematician, an extraordinary theoretical physicist, an astronomer, and an instrument builder. But in this particular solution, he described the curvature of space and time outside of a spherically symmetric body. Now, this solution describes not only the curvature of space, but the warpage of time, which is just time dilatation due to gravity. As I already said, this time dilatation due to gravity leads to the gravitational redshift. Since near the star, time flows more slowly, the frequencies are shifted to longer wavelengths. Karl Schwarzschild had derived an exact expression for the frequency of the redshifted radiation. If nu1 is the frequency emitted from the surface, then the nu2, the frequency as seen by an outside observer, will be related to nu1 by the expression shown over there. In the bracket, you have 1 minus 2 gm by c squared divided by the radius of the star. Therefore, if the star were to have the critical radius r equal to 2 gm by c squared, time dilatation becomes infinite. Time does not flow at all on the surface of such a star. As seen by an outside observer, the frequency of radiation emitted by the star goes to 0, the wavelength becomes infinite, and the star appears black. But there is a fundamental difference between Carl Schwarzschild's black star and John Mitchell's black star. If an astronomer were to orbit John Mitchell's black star fairly close to the surface, he will be able to detect the corpuscles of light. It is true the corpuscles of light will not be able to escape to infinity, but the nearby astronomer will be able to see it. But in the case of a general relativistic black star, no matter how close you are to the critical surface, no one can see any light emerging. Now, this infinite redshift was known at that time as the Schwarzschild singularity. It is not a real singularity at all. It is just a coordinate singularity. But Einstein, in a paper published in 1939, soundly rejected this idea. He wrote, "An essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality." Since Schwarzschild had found an exact solution to his theory, he could not reject the solution itself, but Einstein said it is absurd to think of such situations. Let us now digress for a moment and look at what is happening in the astronomical literature concerning the fate of massive stars. As you all know, in 1930, Chandrasekhar had made a monumental discovery that white dwarfs, which are supported against gravity by the degeneracy pressure of electrons, has a limiting mass, a discovery for which 53 years later, he was awarded the Nobel Prize. What most people do not know is a year after that, Chandrasekhar wrote an even more remarkable paper. The final sentences of his paper are the following. For all stars of mass greater than a critical mass m, the perfect gas equation of state does not break down, however high the density may become, and the matter does not become degenerate. An appeal to the Fermi-Dirac statistics to avoid the central singularity cannot be made. As far as I know, this is the very first time anyone had argued, and Chandrasekhar argued this in a mathematically rigorous manner, that sufficiently massive stars will have no option but to collapse to a singularity. Now, this remarkable discovery by Chandrasekhar provoked the following reaction from Sir Arthur Eddington. Eddington said, the star has to go on radiating and radiating and contracting until, I suppose, it gets down to a few kilometer radius when gravity becomes strong enough to hold in the radiation and the star can at last find peace. Various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd manner. Let us now move to the year 1939, when Oppenheimer and his young student Hartland Schneider studied the implosion of a spherically symmetric star with no internal pressure, etc., but exactly within the premises of Einstein's general theory of relativity. They drew two following conclusions from the paper. One, as seen by an observer far away from the star, as the collapsing star nears the critical radius, its shrinkage slows down till it becomes frozen precisely at the critical radius. It never seems to reach the critical radius. And yet, an astronomer traveling on the collapsing star would describe it very differently. He or she would find that the implosion does not freeze at all. In fact, the collapse proceeds faster and faster till finally it reaches the speed of light itself. Why such diametrically opposite description by two observers, one far away and the other one on the surface of the star? Well, this is very easy to understand from Schwarzschild's solution. As seen by a distant observer, the velocity of the particle falling towards a black hole will be given by the expression shown in the yellow bracket. But if an astronomer were to reside on the blue shell that you see on the figure on the left, very close to the black hole, an infinitely rigid sphere, then that person would see the velocity as given by the expression shown in the blue formula. Now, there is an ancient Chinese saying that one picture is worth 10,000 words. Therefore, let us look at these two equations graphically. What is shown on the y-axis is the speed with which the star collapses. And what is shown on the x-axis is the distance from the center of the star. Rg is the gravitational radius, 2gm by c squared. As seen by a distant observer, the speed of a falling stone will initially increase like in Newton's laws, but then the stone will appear to slow down and it will never reach the surface because the velocity goes to zero as the star approaches the critical radius. But as seen by a co-falling observer, the speed will continue to increase till when the star reaches the critical radius, the speed equals the speed of light itself. Oppenheimer and Schneider concluded their famous paper with the following sentences. When all thermonuclear sources of energy are exhausted, a sufficiently massive star will collapse. The radius of the star approaches asymptotically its gravitational radius, and light from the surface of the star is progressively reddened and can escape over a progressively narrower range of angles. The star thus tends to close itself off from any communication with the distant observer. Only its gravitational field persists. Once a star collapses to the critical radius, 2gm by c squared, it cannot arrest its collapse. According to general relativity, it will continue to collapse till it becomes of zero radius. Therefore, there is nothing inside this black hole. So what is inside a black hole? It would appear that there is nothing inside a black hole. Not quite, but there is something very sinister inside a black hole. After creating the black hole, the spherical star continues imploding to infinite density and zero volume, whereupon it creates and merges into a space-time singularity. A space-time singularity is a place where the curvature becomes infinite, the density of matter becomes infinite, and its volume zero. And space-time cannot be continued past such a singularity. So what is inside a black hole? There is a space-time singularity. But most physicists agreed with Eddington and Einstein that something was wrong with Oppenheimer and Schneider's results. Black holes simply couldn't exist. It just didn't make sense at all. It was widely believed that the Oppenheimer-Schneider result was a consequence of the artificial assumptions they had made. Real stars are not spherically symmetric. There is pressure inside the star. There is energy generation. There are shock waves. All of these things Oppenheimer and Schneider had ignored, even though they had treated general relativity in an exact manner. John Wheeler, who many decades later coined the phrase black holes, felt that general relativity fails inside a black hole. He argued that quantum mechanics would prevent the formation of a space-time singularity. So black holes were soundly rejected, particularly by Eddington and Einstein. The day Oppenheimer and Schneider's paper appeared in Physical Review, World War II was declared, and physicists became busy with other things. Black holes which were rejected were resurrected in the year 1963 when quasars were discovered. The luminosities of quasars were staggering, 10 to the power 46 ergs per second, equaling the luminosity of an entire galaxy consisting of 10 to the power 12 stars. Such a large luminosity, even at the Eddington luminosity limit, would imply that the object must have a mass in excess of 1 billion solar masses. Quasars were variable. Their variability in timescale of few hours suggested they must be extremely compact objects. Therefore, at this point, the only reasonable assumption, hypothesis, for the central engine that powered quasars was that the central engines of quasars were supermassive black holes. So black holes of general relativity with radius equal to 2 gm by c squared became a rather popular thing. The surface of a black hole is known as the event horizon. It is a semi-permeable surface. Things can go into the horizon, nothing can come out to the horizon. Inside the event horizon, there are no allowed trajectories with a constant distance from the center. Once you enter the black hole, you cannot arrest your collapse, and the infalling matter has no option but to continue to collapse till it falls into the central singularity. Remember, we are talking of a spherically symmetric collapse. The next important development occurred in 1964 when the New Zealand mathematician Roy Kerr discovered an exact solution to the geometry of space-time surrounding a rotating star, a rotating black hole. This was the second exact solution after Karl Schwarzschild's solution, which was discovered in 1916. The Kerr solution represents not just one special kind of a spinning black hole, but it represents every spinning black hole that can possibly exist. This was proved by Brendan Carter, a beginning graduate student in Cambridge University, along with Martin Rees and Stephen Hawking and various other people. Now, the space-time in the immediate vicinity of a rotating black hole is somewhat different from the Schwarzschild black hole. There are two surfaces. One is known as the static limit, which is an oblate volume. At the equatorial plane, its radius is 2 gm by c squared. Nested inside it is the event horizon, a spherically symmetric surface whose radius is gm by c squared. The region in between, marked in red in this figure, is known as the ergosphere. Now let us look at this picture from the North Pole or the South Pole. The outer surface corresponds to the point where the coefficient of dt squared in the metric goes to 0. And the inner surface, the horizon, is the point where the coefficient of dr squared in the metric goes to infinity. Now, one of the remarkable properties that emerges from general theory of relativity is that space surrounding a rotating body, it's itself dragged by the rotating body. This is known as the dragging of the inertial frame. Now, this has some very important consequences for someone who enters the ergosphere. In this picture, which is a computer-generated plot, I have tried to show what will happen to a stone or a photon dropped radially towards a spinning black hole from infinity. There is no angular momentum. When the stone or the photon comes in the vicinity of the spinning black hole, due to the dragging of space itself by the spinning black hole, the photon or the stone will be compelled to spiral around the black hole. And when it reaches the horizon, gm over c squared, it will spiral forever. Occasionally, the photon will fall in. Occasionally, it can escape to infinity. Here is a very interesting situation of angular momentum angular motion without angular momentum. Remember, we had thrown in the stone radially. There was no angular momentum. And yet there is angular motion. And this angular motion arises due to the dragging of the inertial frame. Let us now summarize the differences between a non-rotating black hole on the left and a rotating black hole on the right. In the case of a Schwarzschild black hole, inside the black hole, particles and light cannot be at rest with respect to infinity. R equal to constant is not allowed. Particles and light have to move radially towards the center. However, inside the ergosphere surrounding a rotating black hole, phi equal to constant is not possible. Particles and light must rotate around the axis of symmetry. But R equal to constant is possible. Indeed, particles can move with decreasing or increasing R and even escape from the ergosphere if it is sufficiently clever. In the case of the Schwarzschild black hole, as seen by a distant observer, it will take an infinite time for the particle to reach the black hole, which is the event horizon. In the case of the Kerr black hole, particles can reach the ergosphere in a finite time, except at the North Pole and South Pole, because there it touches the horizon, and there, like in the case of the Schwarzschild black hole, it will take an infinite time to reach the poles of the horizon. And now, finally, we come to a truly revolutionary discovery by Roger Penrose. In 1964, Penrose proved a remarkable theorem, an exact theorem using, I think for the very first time, topology in proving a physical theorem. He proved in an exact manner that every black hole must have a singularity inside it. Now let us try to understand this in terms of behavior of light. Penrose himself has drawn these wonderful figures of the light cone being tipped due to strong gravity. But since this is a non-technical lecture, I will give a two-dimensional representation of the tilting of light cones, and this figure is also due to Roger Penrose. Let's imagine we shine a flash of light. That light will escape in all directions in space. The wavefronts will be spherical, and the radius of the wavefront will increase at the speed of light. In the diagram below, I show a cut through the spherical wavefront through the point of emission of light itself, namely the center of the wavefront. As time elapses, the wavefront will become larger and larger. But at all times, the point of emission of light will be at the center of the wavefront. Now let's imagine shining a flash of light at a certain distance from a black hole. Since gravity is not very strong, the light wave will expand in a spherical wavefront, and the point of emission will be at the center of the wavefront as we are used to. But at short distances from the event horizon, the wavefront surface will be displaced from the gravity due to the strong gravity of the black hole. And the point of emission will no longer be at the center of the wavefront. At precisely the horizon, no matter in what direction you shine the torchlight, the spherical wavefront surface will touch the horizon internally. This is known as a trapped surface. Now, once you have reached the trapped surface, once you are inside the event horizon, the expanding wavefront detaches itself from the point of emission. Light emitted in any direction is pulled towards the central singularity. Now, since no observer can travel with a speed greater than that of light, it follows that there can be no stationary observers within the horizon. Every material particle will be pulled inexorably towards the central singularity. Now, Oppenheimer and Volkoff had talked to the central singularity. But what is different this time is that Roger Penrose proved this theorem with sweeping power. He did not assume any idealized condition for the imploding star. He did not assume that the random deformations of the star were small. As Kip Thorne has said, he dealt with every imploding star imaginable. Penrose dealt with stars that actually inhabit our universe. So what is inside a black hole? This time one can say with mathematical certainty that there is a space-time singularity inside a black hole, regardless of any assumption of symmetry. Now, can such a singularity be outside of the black hole? Roger Penrose tried very, very hard to construct models where after a trapped surface is formed, the singularity appears not inside the closed trap surface, but outside the closed surface. But he could not find such a model. Since he could not prove this in a rigorous manner, he stated it as a censorship principle, a cosmic censorship principle. In 1969, he stated that no imploding object can ever form a naked singularity. If a singularity is formed, it must be clothed by a black hole horizon so that no one in the external universe can see the singularity. It is for this remarkable discovery that Roger Penrose was awarded the Nobel Prize 57 years after he had made this discovery. Now, after Penrose proved his theorem, a series of very, very remarkable and mathematically exact theorems were proved concerning the nature of black holes. These went under the name of no-hair theorems. Black holes have no hair, declared John Wheeler. What do I mean by that? Stars have magnetic field. Will a black hole have a magnetic field if the star collapses to a black hole? Ginzburg and Zeldovich in Moscow said, no, the black hole will not have a magnetic field. Suppose the star had a mountain on it. Will the black hole have a little pimple on it? Suppose the star was a cube. Will the black hole be a cube? Zeldovich said, no, no, no. The black hole will be perfectly spherically symmetric. A whole lot of brilliant young physicists went to work trying to prove these remarkable conjectures by Ginzburg, Zeldovich, and others. They finally culminated in a theorem proved in 1972 by Brendan Carter, Stephen Hawking, and Werner Israel. They showed in a mathematically exact manner that black holes are uniquely characterized by their mass, charge, and angular momentum, and nothing else. What about the deformations of the stars? They will all be radiated away as gravitational waves. What about all the quantum attributes of matter that fell into the black hole? Baryon number, lepton number, strangeness number, isotopic spin. Well, all that has been washed away. For the discovery of every one of these conservation laws, a Nobel Prize was awarded in the last century. Interestingly, black holes don't so much violate these conservation laws, they seem to transcend these conservation laws. This discovery prompted Chandrasekhar to react in the following manner. In my entire scientific life, the most shattering experience has been the realization that the exact solution of Einstein's equation, the Kerr metric, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. Soon after that, young Bekenstein, a student of Wheeler in Princeton University, argued that black holes must have enormous entropy. Black holes cannot have zero entropy. Using purely dimensional analysis, Bekenstein argued that the entropy of the black hole must be proportional to the surface area 4 pi r squared of the black hole. He showed that the entropy must be proportional to the surface area, and the proportionality constant will involve Boltzmann's constant, the speed of light, Newton's constant, and Planck's constant. More about that in a minute. Bekenstein argued that if you have a black hole of mass equal to 10 times the mass of the sun, its entropy must be astronomical, 10 to the power 79. And there are lots of black holes in our universe. As Penrose is fond of saying, that almost the entire entropy of the universe resides in black holes that populate our universe. Let's go back to the year 1900. The greatest problem at that time was to reconcile the theory of black body radiation with classical thermodynamics. That problem was finally solved by Max Planck, and he could do so only by introducing a new constant H, which we now call as the Planck's constant, and that was the birth of quantum theory. Bekenstein says the entropy of the black hole is related to its surface area according to the formula that is shown over there. What we are trying to do is to reconcile classical black holes with classical thermodynamics. And Bekenstein says you can do so only by invoking Planck's constant. So perhaps, like we did in 1900, we may be witnessing the birth of a quantum theory of gravitation. But Hawking was very skeptical about this idea. It's rather surprising because one of the remarkable theorems that had been proved about black holes was proved by Hawking himself, where he showed that the area of a black hole can never decrease. A black hole can only increase in its area by gobbling up another black hole. A black hole can never bifurcate and decrease its area. This was reminiscent of the second law of thermodynamics, which says that the entropy of a closed system can never decrease. But Hawking was very skeptical. He argued that a black hole can only have entropy if it had a finite temperature, because according to every textbook, a classical black hole absorbs everything. It does not emit anything. Therefore, it's a perfect sink. You look in any book on thermodynamics, a perfect sink which absorbs everything and emits nothing has to be at the absolute zero of temperature. Therefore, Hawking argued that the temperature of a classical black hole must be 0 Kelvin. Now let us go to Moscow, where the great Zeldovich was coming out with brilliant ideas. He first argued that a spinning metal sphere will emit electromagnetic radiation and particles. Where did these particles come from? We know that in vacuum, there are particle-antiparticle pairs, but you're not allowed to catch them because negative energy states are not allowed. But if you could supply energy to break up a virtual pair, then they will materialize into real pairs. So Zeldovich argued that a spinning metal sphere can give some of its rotational energy to materialize the virtual pairs. Fine. Before proceeding further, let us talk about a very clever mechanism that was given by Roger Penrose for how to extract energy from a rotating black hole. Central to this idea is the notion that inside the ergosphere, which is the red region shown in the figure, particles can exist with negative energy states, which it cannot do in the world we live in. Imagine a blue particle with 10 units of positive energy entering the ergosphere. Having entered the ergosphere, it splits into two particles, a green particle with 15 units of positive energy and a dashed particle with 5 units of negative energy. Now imagine the particle with negative energy falls inside the event horizon, and the particle with increased positive energy escapes from the ergosphere. Well, you now have a situation where there was an incident particle with a certain amount of energy. It got scattered by the ergosphere. It came off with an increased energy. No fraud has been committed. All you have done is to extract energy from the rotating black hole. Remember this. Now let's go back again in time to 1954, when Robert Dicke in Princeton discovered the phenomena of super radiance from atoms. He showed that if you have a group of n excited atoms interacting with light whose wavelength is very large compared to the size of the atomic system, then the atoms can interact with light in a collective and coherent fashion to produce high intensity light. This was super radiance. It was a forerunner to the discovery of lasers. Now, in the Penrose process, which I described a minute ago, an incident particle extracts rotational energy from a spinning black hole. An analogous phenomena occurs when electromagnetic or gravitational waves of sufficiently low frequencies are incident on a black hole in suitable directions. in such a situation, the reflection coefficient of the incident wave can exceed unity. This is the phenomenon of super radiance from black holes. In a series of papers published in 1970 and 1972, the great Zeldovich had made the following absolutely extraordinary predictions. Firstly, he argued that there will be super radiance from rotating black holes, what I just described. Electromagnetic and gravitational waves incident on a rotating black hole in certain modes will be scattered with increased intensity. In the particle picture, not in the wave picture, in the particle picture, this phenomenon of super radiance corresponds to an increased number of particles and therefore to stimulated emission of particles by the rotating black holes. Now, super radiance, therefore, corresponds to a stimulated emission of radiation from rotating black holes. Zeldovich argued that one should also expect a steady rate of spontaneous emission in the super radiant mode. Why? In 1917, Einstein introduced the novel idea of spontaneous emission of radiation. We were all familiar with the concept of stimulated absorption of radiation and stimulated emission of radiation. In the 1917 paper, Einstein argued that whenever there is stimulated emission and stimulated absorption, there must also be spontaneous emission. Why? He couldn't answer at that time. Today we know that an electron jumps from an excited state spontaneously because it is tickled by fluctuations in the vacuum. Einstein showed in the 1917 paper that there is a fundamental relation between stimulated absorption, stimulated emission, and spontaneous emission. It is this relation that leads to Planck's distribution for the spectrum of black body radiation. Therefore, Zeldovich argued, since a rotating black hole can be stimulated to emit, it must also spontaneously emit. During the summer of 1973, Hawking made a visit to Moscow just to talk to Zeldovich. Because Zeldovich had worked on the Russian hydrogen bomb project, he was not allowed to travel to the West. Therefore, everyone and his grandmother went from the West to Moscow to talk to Zeldovich, and Hawking, despite his difficulties, went to Moscow to talk to him in his flat. There, Zeldovich told him about his ideas on spontaneous emission from rotating black holes in the super radiant mode. And then he asked Hawking the following question: will a non-rotating black hole also spontaneously emit? The following year in 1974, Hawking had made his great discovery. A non-rotating black hole will radiate, Mr. Zeldovich. It will emit particles and radiation in all modes, as though it were an ordinary black body at a temperature T, which is proportional to its surface acceleration, surface gravity, kappa. Hawking didn't like this result. He tried his best to make this radiation go away, but it simply wouldn't go away. What convinced him finally was the thermal nature of this radiation. Remember that in the case of black body radiation, the number of photons with frequency nu is proportional to 1 over e to the power h nu over kt minus 1. Hawking found that the number of particles created in a mode omega is proportional to 1 over e to the power 2 pi omega over kappa minus 1, where kappa the surface gravity playing the role of temperature. We know that in the case of black body radiation, the probability of emission is related to the probability of absorption by the principle of detail balance, e to the power minus h nu over kt. In the case of black hole radiation, Hawking found that the proportionality is given by e to the power minus 2 pi omega over kappa. Hawking's discovery, although not mathematically rigorous, makes eminent sense. Recall that when matter and radiation come into thermodynamic equilibrium, black body radiation loses all its memory. It forgets how it was produced. It forgets the frequency at birth, the direction in which it was emitted, its polarization. It remembers one and only one thing, the temperature of the body with which it came into thermodynamic equilibrium. Similarly, Hawking radiation makes sense because the radiation has a thermal spectrum and it remembers only the mass of the black hole. Recall that when matter falls into a black hole, there is a tremendous loss of information. Black holes are uniquely characterized by their mass, charge, and angular momentum. The nature of the radiation emitted by the black hole reflects this tremendous loss of information, like in the case of black body radiation. Hawking radiation makes sense because the radiation has a thermal spectrum and remembers only the mass of the black hole. The important thing to appreciate that even a stationary, non-rotating black hole will radiate. The energy needed for the creation of these particles comes at the expense of the rest mass energy of the black hole. Therefore, as the black hole emits radiation, it will become less massive. Hawking derived the following expression for the temperature of the black hole in astronomical units, where the mass of the black hole on the right-hand side comes in the denominator. Therefore, as the black hole radiates, it will become less massive and therefore hotter. And therefore, it will emit even more. And therefore, its mass will become even less. And therefore, it will become even hotter. We are used to this. Self-gravitating bodies have negative specific heat. So there's nothing surprising about it. What is surprising is eventually this black hole will evaporate away. The event horizon will be gone, and what will remain is a naked singularity. Has quantum mechanics transcended the cosmic censorship principle? Will an evaporating black hole leave behind a naked singularity, which is a terrible thing? Because the naked singularity will introduce into physics an additional element of uncertainty over and above Heisenberg's uncertainty principle. Since particles emitted by a black hole come from a region of which the observer has very limited knowledge, the observer cannot definitely predict the position or the velocity of the particle, or even a combination of the two, as Heisenberg will allow you to do. All one can predict is the probability that certain particles will be emitted. So as Hawking put it, Einstein was doubly wrong. Einstein famously said, God does not play dice. Hawking said, God not only plays dice, he throws them in places where we cannot see. Now let's go back to Penrose's remarkable theorem of 1964. It had a great impact, and indeed, it is at the base of the present revolution in cosmology. Penrose's theorem, namely that every black hole must have a singularity inside it, had a profound impact on Stephen Hawking, who was a beginning student in Cambridge University at that time. It occurred to young Hawking that there is a parallel between the final stages of a collapsing star and the early stages of an expanding universe. Gravity must be very strong. Trapped surfaces must have been formed. Could an expanding universe be a time-reversed version of a collapsing star? The discovery of the cosmic microwave radiation a couple of years earlier had told us that a long time ago, the universe was very small and very dense. Hawking wondered, could the universe have begun from a singularity? Many exact solutions of general relativity had predicted singularities. For example, the Friedman, Robertson, Walker models of the universe had predicted initial singularities and under certain circumstances, even a final singularity. But these singularities were viewed with great suspicion because of the assumption made, namely, that the universe was homogeneous and isotropic in a cosmological scale. When I was a student in Chicago, I remember a very famous paper by two great Russian physicists, Lifshitz and Kalatnikov, who argued very convincingly that in the absence of any anisotropy, the singularity will be washed away. So people didn't take this singularity very seriously. It was at that time, people remember a very important paper published by Amal Kumar Raychaudhuri. This paper appeared in 1955, a few months after Einstein passed away in Physical Review. In this paper, Raychaudhuri had studied the behavior of fluid flow in general relativity. He had derived an equation for the time evolution of the divergence of the velocity field as seen by a co-moving observer. He had drawn three important conclusions in this paper. He had shown that if the energy density is positive, very reasonable, then a contracting fluid flow will continue to contract. This conclusion was independent of any symmetry considerations. Therefore, the focusing effect of gravity was not because of any symmetry that was assumed. It was also implicit in this equation that an expanding fluid flow and a contracting fluid flow were time reversed of one another. People remember these conclusions from Raychaudhuri's paper. And this resulted in Penrose and Hawking publishing a very famous singularity theorem. They made three assumptions in proving this, namely causality is valid, energy density is positive, and either Einstein's theory of gravity or some such geometrical theory is the correct description of gravity and the universe. Under these assumptions, which appears very reasonable to most people, they showed in a mathematically exact manner that the universe could have begun from a singularity or end in a singularity, and both began and will end in a singularity. Was there a beginning to our universe? This question underlies all religions and all philosophies. And yet this question had remained meaningless within the premise of science. Meaningless because there was no way to pose this question in an exact manner within the premise of science. The Penrose-Hawking theorem had made this question meaningful in a mathematically rigorous manner. And thus began the present revolution in cosmology. I thank you very much for your attention.
Thank you so much, Srini. That was such a fabulous talk. We didn't realize that 1 hour had passed. So you are happy to answer some questions now, I hope.
Yes?
Right. So those of you who would like to ask questions in Zoom, could please raise your hand, and or you could also type your questions in the chat box.
Banka, there is a question in chat box by Sri Valluri.
Right.
What would be the analog of Wien's displacement law for black hole radiation?
Right. The question is, what will be the analog of Wien's displacement law for black hole radiation?
Well, I haven't thought about it, but since the spectrum is a black body spectrum, you see, I think it would be the same. In other words, if the body was hotter, then the peak in the spectrum should shift to higher frequency. But this is a conjecture. It's a very interesting question. I simply hadn't thought of it. Sorry.
No, I would have just put it the following way, that change in temperature would mean a change in mass of the black hole. And as you change the mass of the black hole, it will go to a new thermal spectrum. And they are related in the same manner that the Planck law is related in Einstein's displacement law.
I would agree completely.
Another question in the chat box from Abhay asks, does the differential rotation of a star matter when it has become a black hole, or only the total angular momentum of the star that collapsed?
Only the total angular momentum.
Any other questions? So we can go to YouTube chat box if there is any question.
Yes, there are some questions on YouTube chat box, and I will start with the question by Paniveni Uday Shankar. And the question is, how do we compare the singularity at the time of Big Bang to the singularity of that of a black hole?
One is not comparing them. One is saying in both cases, you cannot extend space-time past the singularity. Just as you cannot say what happened to the star once it collapses to singularity, you cannot ask what was there before the universe began in a singularity. So the mathematical significance of the singularity is the same, namely you cannot extend space-time beyond it. Space and time itself came into existence at the singularity. So what happened before the Big Bang is not a question you are allowed to ask in classical theory, because the singularity theorem is proved in classical general relativity.
Okay. There's another a question from Poonam Randev. She's asking, while talking of entropy, we say it is disorderliness. So how can we talk about disorderliness of a black hole?
We are not talking of disorderliness of the black hole. The concept of entropy, if you remember, that Boltzmann introduced, had the following significance. If you had M boxes and you had N balls, the question is, and how many different ways can you throw N balls into M boxes? Now, so the concept of entropy had to do with the number of microscopic configuration corresponding to a macroscopic configuration. So in a macroscopic configuration, lot of microscopic information is lost. Therefore, the notion of entropy was related to the loss of information when you go from quantum physics to thermodynamics. When things fall into a black hole, as John Wheeler was fond of saying, if you had three black holes of identical mass and angular momentum, one was formed with electrons, one with photons, and one with television sets, you cannot tell which is which. All that information that went into creating the black hole has been lost. And it is this loss of information that Bekenstein argued corresponds to the entropy of the black hole.
Okay, Poonam, there are a few more questions on the Zoom. So
Yeah, sure.
And we can get back to you.
Yeah, sure. Sure.
So there is a question from Vikram Khairi. So so I'll just rephrase the question slightly. So Srini, you described how an inertial observer at infinity would not be able to see a star collapsing to a black hole all the way because the time that it takes is infinite as far as the external observer is concerned. The question is, since we are not infalling observers on Earth, will you ever see or observe formation of the black hole event horizon?
Technically, no. But the point is that many of the effects which are special to black holes occur already at a few Schwarzschild radii. So what will be observable astronomically is the behavior of light and the behavior of matter as it falls in towards what may be a black hole. But we will see the behavior at, say, twice the Schwarzschild radius or 1.5 times the Schwarzschild radius. So we will never see, this is a philosophical question to which I don't think I've ever found any convincing philosophical answer. I think it is fair to say that technically speaking, you will never see a star actually collapsing through its gravitational radius. And there I think I have nothing further to add to that.
Thank you. So there is a question from Arunima, which asks, we often hear about tidal distortions near the black hole. Are similar distortions expected near the Big Bang? And if yes, what will be the imprints seen in the cosmic microwave background?
Well, I don't know the answer to the question, but what Roger Penrose has been busy peddling the last 10 or 15 years is that if there had been a previous universe before the Big Bang, then the Hawking radiation or a Hawking explosion of black holes in the previous universe could have left a signature in the microwave background of our present universe. But I must warn you that this conjecture by Penrose is highly controversial, and there's hardly anybody else who believes in this.
There is another question from Sri Valluri. Now, I will probably rephrase this question a bit. Basically, the question is that we did talk about super radiant modes. Is it possible to imagine condensation of the super radiant modes?
I'm sorry, but that is too speculative for me to wander into.
A question from Ritika Chatterjee. How do supermassive black holes form?
The honest answer is we really don't know. There are many scenarios, and they were all stated a long time ago. One is, of course, a hierarchical formation. Galaxies have massive black holes at their centers. Galaxies merge, and through such sequence of mergers, the black hole mass can grow. But then there is the question, why does our galaxy have a 4 million solar mass black hole? How did that form? There is no unique answer to this question. I can only go back to a conjecture that was made by Chandrasekhar soon after quasars were discovered. In 1964, Chandrasekhar was writing a series of papers on stability of stars in general relativity. Very detailed calculation of the stability of stars. And there, in one of the papers, he had a footnote, which was very unusual for Chandrasekhar's paper. And in that footnote, he argued that the supermassive black holes that power quasars could have formed from a supermassive star. Now, what is a star? A star is an object where self-gravity is balanced by pressure of gas and radiation. Now, if the star is very massive, we know that in our own galaxy, then radiation pressure becomes more important than gas pressure. Now, if you're talking about a star, a gaseous star of 1 million solar masses at the center of a galaxy, then it will be supported essentially by radiation pressure, whose gamma, the ratio of specific heat, is 4/3. Now, such a star will be highly unstable because according to Newton's law of gravity, a star, in order for it to be stable against adiabatic compression, must have the ratio of specific heat greater than 4/3. So when matter becomes ultra relativistic, like it happens when a star white dwarf reaches the Chandrasekhar mass, gamma becomes equal to 4/3. That is the reason why the Chandrasekhar limit exists. But the discovery that Chandrasekhar made many years later is that if you had done this problem of white dwarf stability in general relativity, then the white dwarf would have become unstable even if before it reached the Chandrasekhar limit. That is because in general relativity, gravity is stronger than in Newton's theory because all forms of energy contribute to gravity. Therefore, the critical gamma below which matter becomes unstable is not 4/3, but it is 4/3 plus some delta. So the moment you reach that value of the ratio of specific heat, the star becomes unstable. Therefore, in the original conjecture by Chandrasekhar is if you had supermassive stars, by stars, I don't mean stars like we have in our galaxy, but an object which is supported by radiation pressure, then it is prone to collapse due to general relativistic instabilities, and it would directly form a supermassive black hole. This is still a very attractive possibility for the formation of supermassive black holes, which seem to populate in every galaxy. As to why a particular galaxy like M87 will have billions of solar masses, that could arise due to mergers of galaxies. I hope I've made myself at least partly clear.
Right. Yeah, thank you. Prajwal has just made a comment that Priyambada Natarajan and others have argued for the additional idea of direct collapse of massive black holes, black hole seeds early on. So which is similar to what you just mentioned.
Yeah.
So there are a few more questions in Zoom, but maybe we just go to YouTube chat for a moment and we'll come back here.
Sure, Dipankar. So there is a question from Arman Ali. What is causing some black holes to rotate and some to stay stationary?
Stars rotate. Therefore, it is reasonable that if a star were to collapse to form a black hole, then the black hole would have angular momentum. Of course, if the star is rotating sufficiently fast, it would never form a black hole. But suppose you are within that critical rotation rate, then the black hole will form regardless of rotation, and the black hole will be endowed with an angular momentum which it inherited from the star.
Thanks. Another question from Samarth Pardhi. How are Ramanujan's equations useful in black holes?
I have absolutely no idea.
Yeah. There's one more question from Abhijit Das. Can you say something about the naked singularities outside, naked singularity outside an evaporated black hole if it exists?
Nothing more than what I said. The problem, the difficulty with naked singularities is we don't know how to describe them. We don't know what went into them. Therefore, we don't know how it will influence the world we live in. And that is why physicists have never liked singularities. If you remember, every time a singularity was predicted by a theory, it was a realization that the theory was breaking down. For example, when you cool a piece of iron to the Curie temperature, it becomes a ferromagnet, and in the process, the susceptibility becomes infinite. What it means is that your previous description of the spin system has broken down. There has been a phase transition. Similarly, J.J. Thomson's model of the atom, as the electron goes around the proton, it would radiate, and therefore it would spiral in until finally it collapses into the proton, and the atom became unstable. And that signaled the breakdown of classical theory of atoms and classical theory of radiation. And that signaled quantum theory of atom, which of course Niels Bohr invented. So the general feeling is that because general relativity predicts singularities, therefore general relativity itself must break down. Therefore, these singularities may never exist in reality because quantum theory would have replaced the classical theory of gravitation. But that is still a speculation and conjecture because unlike Bohr's theory of the atom, we do not yet have a quantum theory of gravity. So I think it is fair to say that a singularity, a naked singularity would make people feel even more strongly that general relativity must be wrong at very small distances. But what people, very serious physicists like Feldman and others have argued for a very long time that they don't believe in a black hole because it inevitably predicts singularities. So they will question general relativity not at the level of the singularity, but at the Schwarzschild radius itself. And that goes back to Einstein's rejection of black holes in 1939, saying that Schwarzschild singularity simply does not exist in physical reality. The standard argument was that, look, it is only a coordinate singularity. If you go to the right frame of reference, the singularity goes away. But what does not go away is the infinite redshift. So some physicists believe that general relativity is wrong because it predicts infinite redshift, as simple as that.
Thank you. There are a number of questions which are sort of related to some answers that have already been given, so I'll skip some of them. There is one question I think which I think it can be answered to further clarify the concept. The question is, if millions of stellar black holes merge to form a single highly massive black hole, can that be differentiated from a supermassive black hole?
No, it cannot be differentiated.
Exactly. So it is to re-emphasize that only the mass, angular momentum.
Since it's only mass that matters.
That's right.
Please remember that in an astronomical context, the charge of a black hole is irrelevant. We cannot have astronomical bodies with net charges which are very significant because the electrostatic fields they will create will play havoc. So what really matters is just the mass and angular momentum. So it really doesn't matter how the black hole formed.
So that question was from Virendra Yadav. There is a question again from Abhay stating that it is practically quite difficult for a star to have zero angular momentum. So, so likewise, all black holes should therefore have some angular momentum. Is that correct?
Yes. In fact, people believe that most black holes will have, not only will have angular momentum, but they'll have the maximum possible angular momentum it is allowed to have. Because if the angular momentum exceeds a certain critical value, then the horizon doesn't exist. Black hole wouldn't have formed in the first place. So most people believe that black holes of nature will be maximally rotating.
And this sort of goes back to the comment by Chandrasekhar that you had quoted, that the Kerr black hole describes exactly, the Kerr solution describes all black holes in the universe.
Yes. I mean, it's absolutely unbelievable. I mean, that remarkable statement by Chandrasekhar that we cannot have an exact description of even the helium atom, let alone a piece of chalk piece.
That's right.
So we have no exact description of any macroscopic body, and yet we have an exact description of every conceivable black hole that exists in the universe, and there are only two parameters that describe the exact solution. It is really the most remarkable situation in all of physics.
Yes. Poonam, are there any further questions in the YouTube?
Yeah, there are many, but I'll ask some which are not yet answered. So one question from Hariam Prajapati is that how do we calculate the mass of the supermassive black holes?
I think we calculated the same way as we calculate the mass of the sun by using Kepler's laws. At the moment, that is all that we have.
Yeah, it is from the motion of matter around the black hole. And,
that is how Genzel and Guess estimated the mass of this black hole. But I must say that one should not be under the impression that they were the first to estimate it. In fact, using the very same technique, super heterodyning and adaptive optics, Charlie Towns had estimated a mass of 3 million solar masses almost 30 years ago. So it is just that they came up with the most precise measure of the mass at the moment, but it is just using Kepler's laws. As far as I know, no post-Newtonian effects have yet been detected in the motion of the stars orbiting the black hole.
On the same note, Zawakidin Mirtashev is asking, can we apply Virial theorem for estimating the mass of supermassive black hole?
See, as far as gravity is concerned, unless you go within 2 times the Schwarzschild radius or something like that, a black hole is just characterized by a mass. So if the sun were to become a black hole tomorrow, it will have no effect on us except that life will become extinct on the earth, but it will have no dynamical effect on the motion of the earth. Therefore, I suppose all theorems that we are used to in classical mechanics continue to hold unless you come to distances that are so short that you have to take into account the modification of Newtonian gravity due to Einstein. Would that be a fair statement, Deepankar?
Yeah, I think so, because typically the velocity dispersion in the galactic bulge is used to estimate the mass of the included mass.
Yes.
And that is akin to a Virial theorem.
Yes.
So I think it's not very different, really.
Okay. Thanks. There are a couple of questions on entropy, so I'll just ask them together. These are by Sandeep and Surajit Chakravarti. And Sandeep's question is that entropy of black hole of mass, 10 solar mass was much higher. How does it compare to other astrophysical scenario, and what does it physically mean? And then continuing question is that entropy of a black hole is related to the surface area of event horizon. How do we count the microstats on the surface?
Well, with regard to the last point, Wheeler's idea of long time ago is that the fundamental area in the, just as the fundamental unit of angular momentum is h, the fundamental area in quantum gravity will be Planck length by Planck length. So I suppose one way to measure entropy, the Boltzmannian entropy of a black hole, is in terms of evaluating the area of the black hole in terms of the Planck area. So I suggest you that there was a very nice talk that Abhay Ashtekar gave in Bangalore elaborating on this idea some years ago. There have been attempts, people now talk about von Neumann entropy, Boltzmann entropy of black hole, and so on. These are very technical things. I have not kept myself abreast of these things, and therefore I would rather not speculate about them.
All right, we are approaching 11 o'clock, and I think all of you will agree with me that we have had a fantastic morning and a superb lecture by Professor Srinivasan. And on behalf of all of you, let me thank Professor Srinivasan for both this scintillating lecture and addressing all the questions so patiently afterwards. Thank you very much, and have a good morning.
Thank you.